Hello, everyone. Thank you very much for the invitation and for the introduction. So as you have seen in the screen today, I'm going to tell you something about title and abstract. I'm going to talk about what I did in my PhD thesis. I have been studying mostly virtual arting groups, which are an algebraic structure who was introduced recently by Bellingeri, Paris, and Thiel a few years ago. And this structure generalizes virtual braids, who were already known since the beginning of the 2000s, to all arting groups. And I will also tell you about two possible approaches to study these groups. One approach is more like topological, trying to construct cell complexes whose topology is completely described by these groups, classifying spaces. And another approach is more group theoretic or algebraic, trying to study questions like decomposability, isomorphism problem, and rigidity of these groups. So let's get started, and let's introduce the protagonists. Virtual arting groups. So before I give you the definition of virtual arting groups, I would like to give you an example that you may have seen already somewhere, and if not, well, this is going to be your first time. And the example is the virtual braid group on n strands. So the virtual braid group on n strands is defined by the presentation with two families of generators. So with generators, the first family is the family of classical generators, sigma 1, sigma n minus 1. And the second family, tau 1, tau n minus 1, is the family of virtual generators. And the following relations. So I have three different families of relations. The first family says that if two classical generators are adjacent, then sigma I plus 1, sigma I, they must satisfy a braid relation, plus 1. And if they are not adjacent, then they should commute if I minus j is greater or equal than 2. This for all I. The second family of relations involve virtual generators, and it says exactly the same thing. So adjacent generators satisfy a braid relation, I plus 1. Otherwise, they commute, so j to I, if I minus j is greater or equal than 2. And plus, we also have that virtual generators are involutions. So tau I squared is equal to 1 for all I, 1 n minus 1. And then we have the third family of relations that mixes classical and virtual generators. And it says the following thing. So I plus 1. So this is a mixed relation, again, of length 3, if I and I plus 1 are consecutive. Otherwise, we have the classical generator sigma I and tau j commute if I minus j is greater or equal than 2. Okay, so this is the virtual braid group on n strands. I gave you a definition with a representation, so with generators and relations. As we do for classical braids, we could define this group by braid diagrams and equivalence relations on the diagrams. And just to give you an intuition of how it works, the generator sigma I is the classical generator in which I have the strand I plus 1 passing over the strand I in a classical crossing. And if we consider the subgroup of the virtual braid group generated by the classical generators, what we obtain, it is a theorem, it's not obvious, is actually the classical braid group. So we can interpret the braid group as a subgroup of the virtual braid group. This relation is just a Rider-Master move 3. It says that the braid relation is satisfied. The fact that if two crossings are far away in the diagram, I can swap them is just a consequence of ambient isotopy. And so let's see how can I draw the virtual crossing. So the virtual crossing can be drawn as this crossing, in which I do not say which is the strand passing above and which is the one passing below. I just say that these two strands meet in a virtual point. And this is just an analogous of the braid relation, but with virtual crossings. To I plus 1, to I equal to I plus 1, to I plus 1. It's an analogous of the braid relation, but for virtual crossings. And the fact that virtual generators are involution says that if I find two consecutive virtual crossings, then I can detach these two strands and obtain a braid with parallel strands. And the probably trickiest one to understand is the last one, the mixed one. So I'm going to draw it. No, I did a mistake. Okay. So by the diagram point of view, this is the mixed relation. And if you think about it, it's kind of logical, because here we have a strand, this one, that crosses all the other strands only with virtual crossings. And so the principle behind it is that we can make this strand flow, preserving the other crossings, the other classical crossings. So this is a topological geometric interpretation of virtual braids. And these objects were defined for the first time by Kaufman in 1999 in his seminal work about virtual knots and links. And other important contributions were given by Kamada in 2007 and Verschinin in 2004. Okay. So in the same way, virtual braids generalize braids. We add another family of generators, and then we have a relation that describes how these two families of generators interplay. Virtual arting groups will generalize arting groups. So now we're going to define Coxeter arting and virtual arting groups. And to do that, we will need some data to define these groups that are given by a presentation with generators and relations. And this data is provided by a Coxeter graph. So definition, gamma is a Coxeter graph. On a vertex set which is countable if it is a simplicial. Simplicial, it means that I have no loops and no double edges between my vertices, and labeled graph, such that the labels for all couple of vertices in my set of vertices, yeah, was there a question? No. The label MST is either an integer greater or equal than 2 or a symbol infinity. And there is a convention to draw Coxeter graphs if I have two vertices S and T in my set of vertices. If the label is MST equal to 2, then the convention I use is to draw no edge between these two. If MST is equal to 3, then we draw an edge, omitting the label. And otherwise, in all the other cases, we draw the edge and the label if MST is greater or equal than 4, included MST equal infinity. This is the standard notation for Coxeter graphs that we find in Dynkin diagrams for Lie algebras. Now, modern group theory and geometric group theorists use the one in which no edge means infinity, so I should specify which notation I'm going to use through the talk. It's this one. And so now that we have this data, we can define our classes of groups. So given gamma a Coxeter graph on a vertex set S, countable, the associated Artin group A gamma is the group defined as follows. So I give a presentation. The generators of my group are the vertices of my graph. And then I have the following relations. So for all ST in the set of vertices, I say that the alternating word in the two letters S and T of length MST, where MST is the label of my graph, must be equal to the other alternating word of the same length in the same two letters, but starting with the other letter. If you see if MST is equal to 2, then this relation becomes a commutation relation, ST equal to TS. And if MST is equal infinity, then we just interpret this relation as no relation between S and T. And let me just define another class of group which is closely related. The Coxeter group, which we denote by W gamma, is, I should have left more space. Well, so the Coxeter group is the quotient of the Artin group up to the normal closure of the relations in which I ask to each generator to be an involution of order 2. So I have the same set of generators, the same set of relations, plus I add S squared equal to the identity for all vertices. Okay? And now we are ready to define the protagonists of this talk, which are virtual Artin groups. The definition is by Bellingeri, Paris, Thiel in 2023. And if gamma is a Coxeter graph, with set of vertices S, we define two abstract sets, S, a set of sigma S, and T, a set of tau S with S in S, B, two sets in bijection with the set of vertices. The virtual Artin group VA gamma is defined by the presentation with generators S union T. So as I did for virtual braids, we have a family of classical and a family of virtual generators, and the following relations. that will mimic the behavior of braids. So the first family of relations says that the alternating word in the generator sigma s sigma t of length mst should be equal to the other alternating word of length mst. The second family says exactly the same thing for virtual generators. Plus, virtual generators are involutions. So for OS, tau s squared is the identity. And last family of relation is a family of mixed relations that involves both classical and virtual generators. And it says that if I compose the alternating word in the virtual generators tau s and tau t, this time of length mst minus 1 times sigma t, what I obtain is sigma r times the alternating word. So here is tst, here I must have st s, mst minus 1. And here this r is either s or t, depending on the parity of this mst. So if here my word ends with s, then r is going to be equal t. And so is equal, so if mst is even, then this is odd. And so this is t. T if mst is even, and f if mst is odd. Okay, this is the presentation of the virtual orting group. First thing, very predictable. If gamma is this coxograph in which I have S1, S, n minus 1, so I have n minus 1 vertices on a straight path, then the associated orting group, you probably know already, is the classical braid group on n strands. Can you actually see here? There's a shade. The associated Coxeter group is the symmetric group on n elements. The generators are the simple transposition to adjacent transposition generator cycle of length 3 and to non-adjacent transposition commute. It's this presentation for the symmetric group. And if you compare these two group presentations, you see that for this particular Coxeter graph, then the virtual orting group is the virtual braid group on n strands that we have defined in this part of the blackboard. Is that okay? Questions so far?
It took a long time to generalize, didn't it? 24 years.
Yeah, it did. But yeah, it did. So before we delve into the algebraic and topological aspects, let me tell you some properties about these groups. So remark is that there are two natural group homomorphisms. The first one, going from the Coxeter group to the virtual orting group, associating the generator of the Coxeter group to the virtual generator of the virtual orting group. I mean, literally here we see that the relations must be preserved. So this is a group homomorphism. And we can do exactly the same thing with orting group, from the orting group to the virtual orting group, taking the generator and sending it to the classical generator. So these two are natural group homomorphisms. Theorem, again by Bellingeri-Poristiel, is that these two maps, iota A, are injective. So we can interpret both Coxeter groups and Artin groups as subgroups of virtual Artin groups. And this gives a first motivation to start studying these groups because they are larger. And within them, we find Artin groups and Coxeter groups. And in a moment, we will see that there is a nice interplay between Coxeter groups and Artin groups inside virtual Artin groups. And there are also two crucial group homomorphisms that we always use here. So the following homomorphism we have a first homomorphism. So these two are two projections from the virtual Artin group to the associated Coxeter group. We go from the virtual Artin group to the Coxeter group, and we kill the classical generator, and we just send the virtual generator to the corresponding generator for the Coxeter group. You can check that this is a group homomorphism, but we can also do this. We can also send both the classical and the virtual generator to the generator of the Coxeter group. If we were talking about virtual braids, this would be the group homomorphism that takes a braid diagram and associates the permutation that you can read by following the strands in your diagram. So these are both group homomorphisms, and definition, we call the kernel of pi k kVA pure virtual Artin group. Don't ask me why this is the name. That's just how it is. And the other kernel of this other map, pi p, is the pure virtual Artin group denoted by PVA. And these two normal subgroups of virtual Artin groups are just crucial. All the results that we can find about virtual Artin groups pass through these two normal subgroups. And thanks to these two projections, what you can see is if you call G one of these two subgroups, no matter which one, so either PVA or KVA, then you have a short exact split sequence you project onto the Coxeter group. And you can observe that this map here, iota W, is a section for both. So here it's either pi k or pi p, depending on which group you're using. And here is iota W, which is a section of both. So you can write the virtual Artin group, VA gamma, as a semi-direct product of this kernel, PVA or KVA, depending on what you want to do, times the Coxeter group. And this structure of the virtual Artin group as a semi-direct product of groups is very helpful. And this is what makes us understand the group better, and also find some results about virtual Artin groups that are not known for classical Artin groups, thanks to this semi-direct product structure. Yes? Okay, so this is a misleading suggestion, but virtual Artin groups in general are not virtually Artin groups, except in spherical type cases. I will see it in a moment. But the inspiration was virtual braids. So they generalized virtual braids, and they decided to call them virtual Artin groups because it was like a copy of virtual braids. But yeah, in general, it has nothing to do with finite index subgroups and so on. Even though one of these two subgroups, the KVA, is itself an arting group. So there is sometimes a finite index subgroup when the Coxer group is finite, which is an arting group. I'll say it in a second. Okay. Yes. Exactly. And this is what the next part of the talk will be about. So just a few more things about virtual arting groups before we start asking interesting questions. So another thing, some results in the paper by Bellingeri, Boris, and Thiel. One result that I mentioned a few seconds ago is that this kernel, KVA, is actually an arting group with respect to some Coxer graph that I will not define now, but it is explicitly constructed starting from gamma. So if you give me gamma, I can tell you what gamma hat is. And this is explicit. And so when the Coxer group is finite, then there is a finite index subgroup, which is an arting group. And in particular, the generating set for this arting group is in bijection with a set called the root system of a Coxer group. And this action by conjugation of the Coxer group on the kernel of the homomorphism is the action of the Coxer group on its root system, which is something that we understand and we like. And in the same paper, they also find a presentation for the other kernel, PBA, which also has a generating set in correspondence with this root system. I will not give the details here. And they are also able to find, for instance, the center of virtual arting groups that is always trivial. And this is an example in which a result about virtual arting groups is quite straightforward, while it is a long-standing conjecture for classical arting groups. So the center of arting groups is conjectured to be trivial in general. I mean, there are some cases in which it is known to be trivial, or a spherical type in which it's not. But this is a long-standing conjecture, why for virtual arting groups, thanks to this semi-direct product structure, we are able to determine the center. And now we are gonna talk about the second part, which is decomposability. Sorry, pardon, could you repeat? The spherical type ones, yes, but the non-spherical types are conjectured to have trivial center. Rugs are not spherical because the rugs have trivial center.
You join a vertex to everything else. Right.
Yeah, exactly. If you're defining graph as a product with a cleat, then that cleat will be the center of the rag. If your rag is a star on a single vertex, then the center of the rag is a single subgroup generated by that central subgroup.
You want an irreducible answer.
Yeah, irreducible. Yeah, irreducible. Yes.
Graph that the complement.
Yeah. I use the other notation, but
Sure.
So you put an edge when they commute. I put no edge when they commute,
I'm
but
just wondering what the conjecture is then when groups have a trivial.
so in general, except known cases like spherical type or some rags that were the ones you were talking about, the center is conjectured to be trivial. And also it is implied by another famous conjecture, which is the K-pi1 conjecture, which is a conjecture about the universal cover of some hyperplane complement. I can be more specific about it. Maybe we can talk about it later. Okay. So now I wanted to tell you something about a question that I've been interested in, which is decomposability. And let's start with the definition. So a group G is decomposable if I can write my group as a direct product with H and K proper subgroups. And it is indecomposable. Otherwise. Okay. Just some examples. Three groups are indecomposable. Simple groups are indecomposable. If you see these direct factors must be normal subgroups, so simple groups necessarily are indecomposable. Z, the infinite cyclic group with one generator, is indecomposable. Another example is the symmetric group on n elements for every n is also indecomposable. But for instance, if you take Z6, then you will have inside a copy of Z3 times a copy of Z2, so this group is decomposable. And another example, which will be the leading example for what we will see next, is if you take the Coxeter group associated to this Coxeter graph with two generators and one edge labeled by 6, this is a finite Coxeter group, which is the dihedral group of order 12. I don't know, dihedral group, the order, is this the order of the group or the label on the 12? Okay. Okay. Just to understand each other. Just to understand each other, this is the group of symmetries of a regular hexagon centered at the origin. And if you see, this group is decomposable as a copy of the symmetric group sigma 3 times a cyclic group of order 2. And these are both Coxeter groups. So this is the Coxeter group with respect to this Coxeter graph, in which you have two vertices, A, B, linked by an edge labeled by 3, and then an isolated vertex. So this dihedral group is decomposable, and we also see that this group is a Coxeter group with respect to two different Coxeter graphs. So the aim now will be studying decomposability for virtual arting groups and also arting and Coxeter groups. And decomposability is not a question interesting per se, is more like a preliminary step to investigate further questions. Like, for instance, a famous question in these classes of groups is the rigidity question, is to understand whether two Coxeter groups can be isomorphic even if the Coxeter graph is not the same. Or other problems like the isomorphism problem and so on. And understanding decomposability of these groups also has some insights about understanding the automorphism groups of this group. So the aim is understanding this property for our classes of groups. And the first thing that we notice is that if I have my Coxeter graph, which is the disjoint union of k connected components, then if you look at the presentation, we say that if there is no edge between two vertices, then the associated classical and virtual generators commute. So you can see that the Coxeter group decomposes as the direct product of the Coxeter groups associated with the connected components of the graph, and the same happens for arting group and virtual arting group. So the moral here is that if we want to understand the composability for these groups, then we should restrict to the case in which the Coxeter graph is connected. Otherwise, we just decompose our group as a direct product on the connected components, and then we investigate the composability on the components. Okay, so now I need some more space. I think I will do it here. So what about decomposability for Coxeter groups and arting groups, which have been studied for way longer than virtual arting groups? So in this blackboard, I will just try to make a summary of the state of the art about what is known about decomposability for these groups. Okay. So as I said, we restrict to the case in which gamma is connected. Okay. And we distinguish two cases. First, when the set of generators, so the set of vertices of my Coxeter graph, is finite. Since the beginning, we didn't restrict to finally generated groups. We may have infinite graphs with infinite numbers of generators. And the reason why we don't restrict to finite sets, but just countable set of generators, is that this kernel KVA is an arting group with respect to some Coxeter graph gamma hat. And this Coxeter graph gamma hat has infinite number of generators. So let's start in the most general case with infinite number of generators, because even if we don't do that, we end up treating infinitely generated arting groups. So the first case is when the set of generators is finite, and we have a further subdivision. The first one is when the associated Coxeter group is finite, which is called the spherical type case. And the other case in which this group is an infinite group. And about Coxeter groups, or arting groups, we know a few things. Okay. We also treat the case in which the set of vertices is infinite. Okay. So starting with finitely generated Coxeter group, which are also a finite group, there is a theorem by Louis Paris in 2007, where he classifies all the cases in which finite Coxeter groups can be decomposable. We have seen an example here. This is a finite Coxeter group which can be decomposed in a direct product. And this theorem says that if gamma belongs to a precise list of possibilities for coxographs, I won't draw all the possibilities, then the associated coxo group decomposes as a direct product, and the decomposition has exactly this form. One factor is the center of the group, and the other factor is the group modulo its center. And in the same paper, he also shows that so this is just the family of spherical type coxo groups that can be decomposable, and the coxo groups that do not belong to this list are indecomposable. And in the same paper, he also shows that if the coxo group is infinite, then the associated coxeter group is indecomposable. So except for the spherical type case, coxeter groups are indecomposable. In this paper, the strategy to show indecomposability strongly relies on the finiteness of the generating set. So this strategy cannot be adapted to an infinite set of generators. But there is another result, another work by Nuida in 2010, using other arguments to say that even when the set of generators is infinite, the coxeter group is indecomposable as a direct product. So the problem of decomposability for coxeter groups has been completely answered. For arting groups, the situation is more tricky. So for spherical type arting groups, which are those arting groups whose associated coxeter groups are finite, there is another work by Paris in 2004 in which he solves the isomorphism problem for spherical type arting groups, and he also shows that in this case the arting group is always indecomposable when the coxograph is connected, for sure. And in more general cases in which the associated coxeter group is not finite, we don't know. It is a conjecture that they are indecomposable, but we don't know that. There are some cases in which it is known. For example, it is known for racks. It can be deduced for affine type arting groups, even though it is not explicit in the literature, but is one of those things that are known to experts. But there's no general strategy. It's a conjecture for the most general case of arting groups. And we know even less if the generating set is infinite. Okay? So this is an example of a question which is very hard to tackle for classical arting groups, but we know the answer for virtual arting groups. And here it is. Theorem. When the coxeter graph is connected, the associated virtual arting group is always indecomposable. And before I tell you something about the strategy to find this result, I would like to tell you a consequence of this. So a corollary is that if I have the disjoint union of K coxeter graph with each one connected, then we have the automorphism group RVA gamma 1 direct product automorphism RVA gamma k. So the direct product of the automorphism groups of the components is a finite index subgroup of the automorphism group of the whole virtual Artin group. And so the moral is that to understand the automorphism group of virtual Artin groups, it is enough to understand up to finite index the automorphism group of irreducible virtual Artin groups, so of those whose associated coxograph is connected. The fact that this theorem implies this other result comes from if I had a decomposition of my virtual Artin group, which was not a decomposition in which the factors are associated to the connected component, then I would have an isomorphism between different decomposition of these two groups, and the fact that the group is indecomposable says that you can only permute the factors, and so you have a group homomorphism from the automorphism group to the symmetric group, and the kernel is the direct product of this automorphism group. And so far, except for virtual braids, the automorphism group of virtual Artin group hasn't been studied. So if you want to think about it, it's a nice thing to do, in my opinion. And about the techniques, so the tools to show this are the following. So recall that one of these two kernels, KVA, is an Artin group with respect to some coxograph. Okay? And this coxograph has many infinity labeled edges, which allows us to decompose this Artin group as an amalgamated product of groups. Okay? This group naturally acts on a tree, which is the tree associated to amalgamated products. We can use Basser theory. And by this action on a tree, we are able to construct an element that I call theta in this Artin group, in this amalgamated product, such that the centralizer of this element in the Artin group is the infinite cyclic group generated by itself. And this has consequences on the decomposability of this Artin group. So this in particular says that the kernel KVA is indecomposable. So we end up answering to this question for infinitely generated Artin groups when the associated coxograph is this gamma hat here. And the fact that we have a normal subgroup inside our virtual Artin group that is indecomposable, plus another ingredient, which is the fact that the centralizer in the virtual Artin group of this KVA is trivial. So these two things imply the fact that the virtual Artin group is indecomposable. So the techniques that we used are essentially action of amalgamated products on trees. Okay, how much time do I have left? Ooh. I said, okay, I was very quick then. Okay, so I realized this is quick, but this is like the list of steps to get this result. And in the 10 minutes I have left, or maybe now they are 9, I will try to tell you something about the other approach, which is more topological. So the last part of the talk is, as I promised, classifying spaces for these two normal subgroups, PVA and KVA. And I would like to start with a work that motivated my PhD project, which is a work by 2006 by 4 authors that are Bartholdi, Enriquez, Eitingolf, and Rains. So these 4 authors construct a CW complex, a cell complex that I will call omega n. And they show 2 things. The acronymous makes beer. I love it. So this is the beer space in the literature. So they show that for any n, the fundamental group of this complex is the pure virtual braid group on n strands, which is the kernel PVA in the case of virtual braids. And they also show that this space, omega n, is locally cat 0, which is a condition on the metric. And the fact that the space is locally cat 0 implies that the universal cover of this space is contractible, so that the space is aspherical, namely the higher homotopy group vanish. And so it implies that this CW complex is a classifying space or a K-pi1 or a Eilenberg-MacLane space or other synonymous of this. Let me write a K-pi1 for the pure virtual braid group on n strands. Okay, so the original project of my PhD was trying to generalize this space in order to get a classifying space for all pure virtual Artin groups. But doing that and studying this construction, we found a mistake here. So unfortunately, omega 3, so already for n equal 3, is not locally cat 0. Which means that we can no longer use this tool to imply that the universal cover is contractible, but it could still be true. It's not an if and only if. And yes, no, for 3, and this is a very good remark. I'm sure it works also for a higher dimension, but I don't know how to prove it. So we can talk about the difficulties next. So after this, we have 2 questions. So the first question is if we can generalize omega n to all Coxeter graphs. And the second question is this omega n a spherical? So is it a classifying space? And the answers to these two questions are yes and yes. And to get the answer, we have to involve another very famous space that is widely studied in literature, which is the Salvetti complex, which is linked to the famous K-pi1 conjecture for arting groups. And so essentially what we do is, so we construct a cell complex omega gamma, and we show the following. We show that the fundamental group of this cell complex is always the pure virtual arting group. So this is a good candidate to be the classifying space. We also show that for gamma, the Dynkin diagram, an minus 1, then this space coincides with the original Beer space. So it is indeed a generalization. And another thing that we show is that when gamma is of a fine type, which is a condition on a bilinear form associated with gamma, or spherical type, which means that the associated Coxeter group is finite, then this space is aspherical. And to answer your, which question, I don't remember, if we can get results about the virtual braids, talking about virtual arting groups, yes. So this implies that this space that they constructed is aspherical, even though it is not locally zero. And the other result about decomposability says that virtual braids are indecomposable as a direct product of subgroups. And in the last 2 minutes, I'll just try to give a rough intuition about how this construction works. So we have said that there are these two kernels, KVA and PVA. Okay? This KVA is an arting group with respect to some Coxeter graph gamma hat. And there is a very famous candidate to be the classifying space of arting groups, which is a space called the Salvetti complex. Of gamma hat. So the K-pi1 conjecture says that the Salvetti complex, so we know that this Salvetti complex has the good fundamental group. So we know that the fundamental group of the Salvetti complex is always the associated arting group. The K-pi1 conjecture states that the Salvetti complex is aspherical. And so it is a classifying space. We show that when gamma is of spherical type or affine type, the Salvetti complex, I keep doing a bar, the Salvetti complex satisfies the K-pi1 conjecture. And so this space is aspherical. And what we do is we have here our subgroup PVA, and here we have KVA. Here we have our complex omega, and here we have our complex, the Salvetti complex of gamma hat. These two subgroups have a common subgroup, which is their intersection. So there will be cover of this space whose fundamental group is this group, and the same, there will be a cover of the Salvetti complex whose fundamental group is this intersection of groups. So let me call this cover omega bar and Sal bar of gamma hat. And what we do is showing that these two coverings are the same. So there is a cellular isometry between these two. So up to relabeling the faces, these two complexes are the same. And so since we know for spherical type and affine type that this space is a spherical, these two share the same universal cover. And so we also deduce that this is a spherical for gamma affine type or spherical type. That was very quick and chaotic. I'm sorry. I will stop here. Thank you very much.
Virtual grades, like grade groups are as few continuous phrases, right? It's
Ah.
very natural.
A very good question. There's a version of that for welded braids, which is a quotient of virtual braids. I don't think there's so far an interpretation of virtual braids as a pi1 of some configuration space, but I think there's someone working on it. So at present, no, there's not an interpretation about it, but very good question. Yes? It's one of my ongoing projects. At least for a spherical type or a fine type, yes, they are. Quite convinced that they are. I mean, we have to fix some details, but yeah. Thank you. I think this question hasn't been investigated yet. So, I mean, the groups have been defined 3 years ago, so there's not much literature about them. I think nothing is known about a cylindrical property. Also about cohomology or cohomology. No, I think nobody did it. And I know nothing about it. So far, from my experience, I would say they are easier thanks to this semi-direct product structure. But maybe there are some questions that are easier to tackle for arting groups. I don't know, especially spherical type arting groups have good properties like with Garside structures and solution to the word problem. So maybe if you want to exploit those techniques, then it's easier to work with classical arting groups rather than with virtual arting groups. But for like general questions, so in my experience, what it's easier in virtual arting groups is to get results on general Coxeter graphs. Because in Coxeter groups and arting groups, you always end up like dividing spherical type or FC type or even cases, or while as it happened for the decomposability result or for preliminary steps to get this result, like for virtual arting groups, they are more uniform, like everything that works for spherical type should work in general. But maybe this is just my opinion because I like them, so I consider them easier. I don't know. Yes? Oh no, because this gamma hat is very specific. It has many infinitely labeled edges, and even if you erase all the other edges and just keep the infinitely labeled, the graph is still connected. So it's always an amalgamated product, and I don't know, many arting groups are not. So no, there's any hope that these arting groups will be all arting groups. There are so many arting groups that are not expressible as this AGA. If this was the question, was it? No. No, I don't think so. It's very specific. Like I can give you an example. The vertices of this gamma hat are always the roots of the root system. So for instance, if your graph gamma is just 2 generators and relation 3, so the associated Coxer group will be the symmetric group on 3 elements, then gamma hat is, it has 6 edges because there are 6 roots. And then you have this 2 triangles with 3, 3, 3, and then all infinities everywhere else. It's very specific, yeah. So I would say that there are lots of, even FC type that can't be expressed like a gamma hat. That would be too good to be true. Thank you.